All right, everyone, welcome back to our mechanics and materials sequence. And in this video, I'm gonna do a simple example problem on how to calculate shear stress in beams. And what we're gonna do is basically apply the transverse shear formula here and calculate the shear stress in a beam. And so I got a simple structure here: simply supported beam at ends A and B with a 200-pound per foot load and 8-foot long beam right here. Here's what my cross section looks like. So if I were to take a view or a cut here, if I could actually look this way on the beam, I would see here this cross section view. What we want to do is find the maximum shear stress in the beam. And so the first thing that we need to do here in order to find this maximum shear stress is, one, do our statics and draw the V diagram, the shear diagram here. And so this is pretty simple. You know, this structure, the boundary conditions, as far as we are concerned, are symmetric because AX is going to be 0. So the boundary conditions are symmetric and the loading is symmetric. That means each of these, A and AY and BY, are both going to be equal. So 200 times 8 gives me a resultant here of 1,600 pounds, which means that AY will be equal to 800 pounds. They'll take half, and BY will also take half. So that hopefully that makes sense to you. When the loading and the boundary conditions or reactions are symmetric, then you're good to go, right? And now we want to draw the shear diagram. And that shear diagram, we're going to use a graphical approach, which shouldn't be too foreign to anybody here watching this video here. But here in the shear diagram, V, and we'll put units of pounds force right here. And here, what happens is you start from here going left to right. AY goes up to 800 pounds right here, and then down to minus 800 over here. And so this will be linear, and hopefully I can draw a straight line, and that looks pretty straight. And this should be at midspan. This distance right here should be L over 2 or 4 feet. Okay, so this should be 4 feet here. So our maximum shear occurs at the support. So max shear at supports. That's something we note. Max shear along the length of the beam is at the supports. And within a cross section, the maximum shear stress, max shear stress in a cross section, occurs when it's linear elastic at the neutral axis of my cross section here. And so I expect my max shear stress to occur right where this 2-inch line is right here, but this being 2 inches, my neutral axis, because this is a symmetric shape, is right here. This is my neutral axis, and my max shear stress will occur there at that location. So with that being said, since we know where the max shear occurs and what the maximum shear stress, where that is, we can go ahead and proceed. And those are really the two important things that you have to figure out. So the next thing you want to do, once you can understand where the maximum shear stress is and where it occurs, you want to do some section properties or geometric properties of the cross section. And looking at that formula here, this tau equals VQ over IT. The geometric properties are I, T, and Q right here. Okay, so I is the moment of inertia of the entire cross section about the neutral axis. So if I look at this cross section over here, this thing right here is symmetric. Even the holes that if I were to look at this, so let me isolate this. I've got a computer, so let me bring it, copy. Bam, move this down. You can fast forward this. No one's offended if you do. But here, if I look at this over here, this neutral axis of the whole thing is just, I can look at, instead of trying to do parallel axis theorem a quick way, because again, the cross section is symmetric about the neutral axis, and this red square has the same centroid as my voids here. These share the same neutral axis, if you will. I can just say that about the neutral axis, the moment of inertia, is 1/12 the large square, 1/12 base, which is 8 inches times the height. 8 plus 2 plus 2 is 12 inches cubed, minus the holes, which is minus 2 holes times 1/12 the width of this hole, which is 8 minus 2 So 3 times the height of that hole, 8 inches cubed here. And this, if when I work this out, will give me 896 inches to the fourth right there. Okay, so that's one thing that's done. So bam, done. The thickness that we're going to use in this is where we're interested in the maximum shear stress. And in this case, we're interested in the maximum shear stress at the neutral axis. So we want this thickness right there through the cross section. So in this case, this is 2 inches because that's where we want the maximum shear stress, or that's where the maximum shear stress occurs. And now we want this first moment of area. And for this first moment of area, let me get rid of some of these lines here, make this drawing a little bit clearer. Here, right here. Okay. And so here, if I fill these back in, right here, here's my neutral axis again right there. Okay. So the Q is the first moment of area of the entire cross section above or below where you want the shear stress. So A prime times Y bar prime. Maybe you've seen it like this right here. So in this case here, for Q, I can look at either, I want the shear stress right here on this line, right here at the neutral axis. So I can look at the area, everything above or everything below. And if I choose everything above, all I got to do is break this up into 2 elements. I want to break it up into this element here, the flange, and then this portion of the web. Let me use purple for the second area right here. Bam, like this. And I need to know the distance of the centroid of each of these from the neutral axis. So I'll call this y1 prime. This will be area 1. And then the centroid of this area will be y2 prime right there. And really, you just got to fill in. I have 2 areas, so I'm going to have 2 things I'm going to sum up. And so here, this would be for the first, for this first area, which I'll call this one 1. Call that 1. And this one will be my 2 area here. So here, I would have, A1, Y1 bar prime plus A2, Y2 prime, where Y prime is the distance to the center of that area from the neutral axis. And so here, this would just be A1 is this purple zone right here, which would be 4 inches times 2 inches, that's the area, times the distance to the neutral axis, which would be here, again, if this is 4 inches, this Y1 prime is 2 inches, plus the area of this yellow, which would be 8 inches times 2 inches, times the distance from the neutral axis to the centroid of that area 2, or that yellow zone. And that would be 4 plus 1. That's going to be 5 inches. And I just sum that up right there, and that's going to be 96 inches cubed. And once I've got all that, everything now is just a straight up plug and chug. So here, if I plug and chug over here, so this would be part 3, plug and chug. So apply tau equals VQ over IT right here. And this tau max is equal to the shear at that location, which was 800 pounds, times Q, VQ, 96 inches cubed, over the moment of inertia, which is 896 inches to the fourth, times T, 2 inches, which is equal to, and if you run this through your calculator, I got 42.86 PSI right there. So hopefully that was pretty interesting and useful for you, at least for a first application. And maybe we'll do something a little bit more interesting and exciting. And perhaps, I think one thing I would recommend is you try to draw the stress profile for this cross section and see what that looks like. And maybe I'll do that in another video. All right, enjoy. See ya. Or the shear stress profile for this video. All right, take it easy. Bye.